Imagine an AI that doesn't just guess the next word, but drafts an entire paragraph all at once. And then it realizes it made a logical error at the end and actually rewrites the beginning of its own thought process before it ever even shows you the text.
Yeah, it sounds like science fiction, but that is exactly what Google DeepMind has just achieved.
Right. So welcome to AI Paper Slob. Today we are doing a deep dive straight into the DiffusionGemma technical report. And, for those of you building and deploying models right now, I want to give you the immediate 60-second download on why this paper is just absolutely lighting up the ML community.
Let's hear it.
So DeepMind has built an experimental open-weight language model that completely abandons autoregressive next token prediction, entirely.
Right, they threw it out.
Exactly. Instead, they use discrete text diffusion to process blocks of 256 tokens in parallel. And they built this on top of the Gemma 426B A4B mixture of experts architecture.
Which is already a beast of a model.
Right. And the result? It achieves roughly 1,500 output tokens per second on a single H100 GPU. That's at FP8 precision, with a batch size of just 1.
That speed is honestly hard to wrap your head around.
I know, it's averaging nearly 20 tokens per forward pass. That vastly outperforms state-of-the-art speculative decoding, while still retaining its thinking mode and all those long context capabilities you need.
It really fundamentally rewrites the physics of how we serve large language models. I mean, we are looking at a system that breaks the absolute speed limit of modern LLM inference.
By shifting the bottleneck, right?
Exactly, by shifting the execution bottleneck entirely.
Let's actually examine why this architectural shift was necessary for inference scaling. Because if you're serving language models right now, you are intimately familiar with the autoregressive bottleneck.
Oh, painfully familiar.
Yeah, it's the classic von Neumann bottleneck. Your GPU's arithmetic logic units are, they're essentially a fleet of Ferraris stuck in traffic.
That's a great way to put it.
They're just idling, right? Waiting for the model weights and the KV cache to arrive from the high bandwidth memory.
Right, because autoregressive, or AR generation, is strictly sequential. You generate token n, and that is the only thing that allows you to generate token n plus 1.
You can't skip ahead.
No, you can't. The actual matrix multiplications on the GPU, they take fractions of a millisecond. The delay is entirely the memory bandwidth. So you are spending all your time shuttling data back and forth just to do a tiny amount of math.
Which is wild when you think about how powerful these chips are.
It is a severely memory-bound regime. Now, obviously, the community has tried to patch this with speculative decoding.
Right, things like multi-token prediction.
Yeah, MTP, where a smaller, cheaper drafter model guesses a sequence ahead, and then the big model verifies it in parallel.
But, speculative decoding hits a very hard mathematical ceiling, doesn't it? Because of suffix decay.
Yeah.
The drafter model's accuracy just falls off a cliff the further ahead it tries to guess. Even with state-of-the-art MTP implemented on that Gemma 4 base, you are still only yielding about, 3 to 6 actual accepted tokens per forward pass?
Yeah, that's about the limit. You just can't push it much further.
It's kind of like, imagine a chef in a kitchen. AR decoding is like a chef walking all the way to the fridge to fetch a single ingredient, walking back to the counter, and then realizing they need something else and walking all the way back.
It's terribly inefficient.
Right. But what DiffusionGemma does with discrete text diffusion is entirely different. We aren't having a smaller model guess the future ingredients. It's like bringing a massive basket of 256 ingredients to the counter all at once.
And refining them simultaneously.
Yeah.
And that detail, the discrete multinomial diffusion, is crucial for technical practitioners to really understand.
How does it differ from, say, image diffusion?
Well, this is not continuous diffusion like stable diffusion, where you are adding Gaussian noise to a continuous latent space.
Right, because language isn't continuous.
Exactly. Language is inherently categorical. You can't have a token that is mathematically halfway between the word apple and the word car. It just doesn't exist.
So how do they corrupt the text then?
Instead of Gaussian noise, DiffusionGemma uses transition matrices to randomly flip categorical token IDs in a vocabulary. It corrupts the text by sampling from a uniform distribution.
Just total random static, essentially.
Exactly. The model then learns to reverse that process, predicting the clean categorical distribution for all 256 positions at the exact same time.
Wow. And by doing this, DiffusionGemma shifts the entire execution profile from being memory-bound to being massively compute-bound.
Which is exactly what you want on an H100. It leverages the parallel compute capabilities of modern GPUs that AR models just leave stranded.
But, from an engineering standpoint, this immediately raises a massive architectural question.
Yeah.
It's one thing to generate 256 tokens in a single parallel block.
Yeah.
But how do you handle long, open-ended context?
Oh.
Like, if I'm passing a 10,000 token prompt and having a multi-turn chat, how do you string those 256 token blocks together without destroying the sequence history?
That's the tricky part.
And more importantly, how did DeepMind build this without sending tens of millions pre-training a brand new diffusion model from scratch?
Well, the brilliant part is they completely bypassed the pre-training costs. They warm-started directly from the Gemma 426B AR weights.
Wait, they use the autoregressive weights for a diffusion model?
Yes. To make that work without breaking the underlying logic of the transformer, they functionally inverted the architecture compared to traditional encoder-decoder models like, say, T5.
Okay. Inverted how?
So DiffusionGemma uses the exact same transformer backbone for two entirely distinct roles. First, it acts as a causal encoder for the prompt context and the sequence history.
So it processes that left to right just normally?
Exactly, to build your standard KV cache. But then it flips its role and acts as a bidirectional decoder for the 256 token canvas generation.
So we are effectively siloing the causal history from the noisy canvas. It's looking at the history causally, but looking at the current 256 token block bidirectionally.
That is the core mechanism. It starts with that canvas of 256 uniformly noisy tokens. Then it iteratively denoises that canvas, cross-attending to the KV cache of the causal history.
And because it's bidirectional within that specific block?
Token position 10 can look at token position 250 to figure out what it should be.
That is wild.
Right. And once that entire 256 token block is fully denoised into clean text, the engine takes that finalized block, passes it back through the causal encoder, appends its keys and values to the permanent KV cache, and then just initializes the next noisy block.
The elegance there is that because it shares that Gemma 4 backbone, the weights still fundamentally understand causal generation.
Yes, they haven't lost that ability.
The paper actually notes it operates in a dual mode, so you can dynamically route requests at runtime. Like if a specific system prompt requires standard autoregressive generation, you can just serve the model causally without swapping weights.
Which is a tremendous operational advantage if you are managing dynamic serving environments. You don't need two separate models taking up VRAM.
Right. But we definitely need to address the training pipeline because repurposing AR weights for bidirectional attention is, it's not trivial.
Not at all. Gemma 4 wasn't trained to look at a canvas of pure noise. It was trained to look at perfect, clean text. You have to fundamentally alter how the model resolves dependencies.
So let's break down that two-stage pipeline. Stage 1 is the supervised fine-tuning, or SFT phase. And they achieve this using less than 10% of the AR model's original training token budget, which is incredibly efficient. During SFT, they introduce a block diagonal attention mask. Can we drill down into the mechanics of that mask?
Sure. When they apply the block diagonal attention mask, they are essentially isolating the 256 token canvas from the rest of the sequence during the backward pass.
Okay, so it can't cheat by looking outside its block.
Exactly. It forces the model to strictly resolve local dependencies within that specific block. It learns how to take a uniform distribution of noise and map it back to the target text by looking at all 256 positions simultaneously rather than just looking at the previous token.
Got it. Now that SFT phase yields a model that can generate text. But from what we know about early text diffusion, it's going to be incredibly slow, right?
Oh, painfully slow.
Yeah.
An SFT-only diffusion model needs dozens, sometimes hundreds of denoising steps to get high-quality output.
And if you try to force an SFT model into a low-latency few-step regime, the generation quality just completely collapses into repetitive token loops.
Yes, it just falls apart.
So how did they compress the step count? Because historically, in diffusion, reward-driven alignment and sampler distillation are two entirely decoupled sequential stages.
DeepMind bypassed that entirely. And honestly, this is arguably the major technical breakthrough of the entire paper. Right, stage 2, which is SDRL, that stands for Sampler Distillation and Reinforcement Learning. It is a unified online learning phase. They optimize both axes concurrently.
But at the same time.
Yes. A single gradient update is simultaneously maximizing the reward, which improves the generation quality and alignment while heavily penalizing the number of denoising steps required to get there.
What I found fascinating about SDRL is the implicit curriculum learning effect. The algorithm just naturally paces itself.
It really does.
As the model trains on these gradients, its predictive entropy drops. It becomes more mathematically confident in its outputs earlier in the denoising process.
Right.
And because of their adaptive stopping mechanism, that drop entropy triggers the generation to terminate faster and faster during training.
It creates a self-reinforcing loop. The training distribution naturally shifts towards shorter and shorter denoising trajectories. So the model organically specializes in the few-step regime without engineers having to, hard-code a strict step reduction schedule.
Let's pause on the concept of predictive entropy for a second, because that leads us straight into how the inference engine operates in production. The training pipeline compresses the necessary steps, but at inference time, how does the model actually know when a block of 256 tokens is finished?
It relies on an entropy-bounded sampler. First, they apply a temperature annealing schedule that scales down from 0.8 at the start to 0.4 at the end.
Why start high and go low?
Well, in the early, highly noisy steps, the temperature is higher to allow diverse token exploration. You want to avoid getting stuck in local minima in the discrete token space.
Makes sense.
But as the semantic structure solidifies across the block, the temperature drops to aggressively commit to high-confidence sequences.
And layered onto that annealing is the adaptive stopping heuristic. Now, the sampler has a maximum hard budget of 48 steps per block.
But it almost never uses all 48.
Exactly. The denoising terminates early if two specific conditions are met simultaneously. First, the mean predictive entropy across the entire canvas has to drop below a threshold of 0.005. And to be clear on the math here for everyone listening, that entropy is measuring the uncertainty over the multinomial distribution of vocabulary for all 256 positions.
Exactly. A mean entropy below 0.005 basically means the model is almost absolutely certain about the token IDs across the entire block.
And the second condition?
The second condition is that the deterministic predictions, meaning the argmax token IDs from two consecutive denoising steps, must be completely identical.
So it's effectively signaling, I am highly confident, and my confidence hasn't shifted a single token since the last iteration.
Yes. If both conditions are met, it finalizes the block and moves on.
This means the model is dynamically allocating compute based on task complexity. That is a massive paradigm shift.
It really is.
In a traditional AR model, generating 256 tokens costs exactly 256 forward passes. It doesn't matter whether it's outputting a highly complex mathematical proof or just copying some boilerplate JSON.
It's a flat cost. But with DiffusionGemma, it averages only 12 effective denoising steps across the board.
12 steps instead of 256. But that average kind of obscures the variance, which is where it gets really interesting.
Oh, absolutely. Harder algorithmic tasks, like those on Live Code Bench, they organically require more steps to converge.
Because code is brittle.
Exactly. Code syntax is highly brittle. A single missing parenthesis breaks the entire compilation, so the predictive entropy remains elevated until those exact syntactic dependencies resolve across the block. Conversely, simpler natural language tasks converge much, much faster.
And there's an incredible side effect of the SDRL phase that the researchers call emergent conciseness. Is that an artifact of the reward function explicitly penalizing length? Or is it just mathematically easier to denoise shorter text rapidly?
It's likely a combination of both. By rewarding the model for maximizing alignment scores in the fewest possible denoising steps, the RL algorithm discovers that the optimal policy is simply to get straight to the point.
Stop rambling, basically.
Yeah. It learns to produce correct answers in half the total tokens compared to the SFT checkpoint.
That is an incredible multiplier on inference speed. You're taking fewer steps per block, and you're outputting fewer blocks overall.
It compounds beautifully.
But I do have to push back here on the hardware math because the claims almost sound too good to be true. Gemma 4 is a mixture of experts architecture.
Right.
In standard AR generation, if you feed it one token, it routes to maybe 8 experts. If you throw a canvas of 256 completely different noisy tokens at it simultaneously, you're going to trigger massive memory overhead by activating almost every single expert in the layer at once.
That's a very fair point.
How does that not entirely wipe out the latency gains?
It's a highly valid concern, and the paper provides a very transparent analysis of the GPU kernel time to address exactly that. So a single DiffusionGemma step processes 256 times more tokens than an AR step, but it is only 3.2 times slower on the clock.
Let's break down where that 3.2x slowdown comes from, because that is the actual cost of the parallelization.
The primary bottleneck is exactly what you identified, the MoE routing. While standard AR activates 8 experts, DiffusionGemma activates roughly 84 unique experts per block.
Okay, yeah, that's a lot more.
Fetching all those expert weights from high bandwidth memory simultaneously is computationally expensive. The second overhead is the sampling operation itself. Doing a full Canvas softmax over a vocabulary of 262,000 tokens takes 3.06 milliseconds.
Compared to what in AR?
Compared to just 0.56 milliseconds for a single AR token.
And we also have to factor in the attention mechanism. They use flash attention for, which is obviously highly optimized, but bidirectional attention across a 256 token block requires significantly more FLOPs than just a single causal lookback in AR.
It does. But when you calculate the net throughput, the math works out overwhelmingly in DiffusionGemma's favor for single-user or low-batch serving. At a batch size of 1 on an H100, DiffusionGemma hits 1,456 tokens per second.
Wow.
That is a 4.8x improvement over a heavily optimized Gemma 4 AR running multi-token prediction.
So it establishes a completely new Pareto frontier for open-weight models. It vastly outperforms things like Nimatron 14B and LEDA 2.1 Flash 100B, and it's aggressively competing with the proprietary Mercury 2 API.
Yeah, it's punching way above its weight class.
If you are currently paying to host a multi-agent framework where LLMs are constantly talking to each other in the background, this fundamentally changes your compute budget. You are moving from a memory-bound cost center to a compute-bound one. But, I mean, what is the crossover point? At what scale does the sheer arithmetic load of diffusion cause AR to win again?
Right, because text diffusion requires so many more FLOPs per step, it eats into the GPU's arithmetic logic units much faster. If you start scaling up the batch size to handle many concurrent users, the AR models eventually regain the throughput advantage.
Where exactly is that crossover?
The crossover point is around 32 concurrent requests.
Ah, okay.
If you are running a massive batched inference server for thousands of API users, standard AR might still be more efficient for you. But for latency-critical applications, agentic workflows, or local edge deployment, this architecture is revolutionary.
It's not just about the raw tokens per second metric, though. Generating all these tokens in parallel fundamentally changes the physics of how the model reasons. Let's look at the emergent properties, specifically bidirectional self-correction.
This is perhaps the most intellectually profound finding in the entire paper. They showcase a logic puzzle about a frog crossing a 25-foot pond.
Let's do the setup.
The frog hops 5 feet a minute, but there's a magical lily pad at 20 feet that teleports the frog back to the 5-foot mark.
It's an infinite loop trap.
Precisely. When you feed this puzzle to the standard AR model, it is forced to generate sequentially. It looks at the prompt and immediately spits out, yes, it is possible.
Because it hasn't thought ahead yet.
Right. It mathematically commits to that answer in the output space. Then, as it starts reasoning through the sequence, 5, 10, 15, 20-foot hops, it realizes it is mathematically trapped.
That's too late.
Exactly. It has already written yes, so it ends up generating bizarre, contradictory reasoning to try and justify an impossible conclusion.
The AR model basically gets trapped by its own left-to-right causal timeline. But with DiffusionGemma, you get a completely different denoising trace. If you inspect the early steps of the 256 token block, it actually trends toward the wrong answer initially, giving high probability to yes.
Right.
But because it is refining the entire canvas bidirectionally, the logical constraints from the end of the thought process propagate backward to the beginning of the canvas.
The parallel generation allows the conclusion and the reasoning to co-evolve. It recognizes the mathematical loop in the later tokens, which actively suppresses the probability of yes in the earlier tokens.
That's amazing.
The model seamlessly converges on the correct answer, no, before it ever outputs a single finalized token to the user.
I look at it exactly like solving a crossword puzzle. If you are forced to guess a sentence strictly left to right in pen, the moment you misinterpret a clue, you make a mistake and ruin the whole board.
Exact.
But diffusion is like filling in a later word, which provides the vertical crowing letters that instantly flag and fix a mistake you were about to make earlier in the horizontal puzzle.
That bidirectional constraint propagation is also why DiffusionGemma is so absurdly efficient at structured output. Think about strict JSON extraction or code debugging, where the syntactic structure is rigid.
Right.
The diffusion process heavily exploits those structural priors. An AR model still has to pay an ON compute cost for every single boilerplate bracket, comma, and indentation.
Which is such a waste of compute.
But DiffusionGemma locks in that boilerplate instantly across the whole canvas and focuses the remaining denoising steps strictly on resolving the semantic payload. It often converges in just 2 or 3 steps.
Which is a massive leap in efficiency for developer workflows. So for the engineers listening, how do you actually get your hands on this? Because DeepMind released the weights under a permissive Apache 2.0 license, right?
They did. Furthermore, they released a hackable diffusion toolkit complete with LoRA recipes, meaning you can adapt this to your own domains on standard consumer hardware.
That's huge. And the paper includes a very compelling fine-tuning example. They trained an 8-rank LoRA, which, for context, adds just 8 million parameters over 2,000 steps on a Sudoku dataset.
And how did the base model do?
The base model completely failed at Sudoku, yielding 0% accuracy. But that tiny, computationally cheap fine-tune brought its puzzle-solving accuracy to over 84%.
That's a massive jump for such a small LoRA.
And they demonstrated it works equally well for domain-specific natural language tasks, like PubMed QA.
It is highly adaptable. But, we do need to address the limitations honestly, as the authors do in the paper. Because they bypassed native diffusion pre-training and relied on a relatively short SFT phase, there is a slight absolute performance drop compared to the Gemma 4 AR base model across standard benchmarks.
I mean, it's an engineering trade-off. You are sacrificing a couple of percentage points of accuracy for a nearly 5x speedup in low batch scenarios.
True. They also note rare instances of token stuttering where the model gets stuck in a loop generating the.
Oh, interesting. Why is that?
This is an artifact of aggressively restricting the denoising steps during SDRL to maintain that ultra-low latency.
I see.
And in multimodal tasks, like on the MMMU Pro benchmark, the model sometimes forgets to output the closing thought tags.
That makes mechanical sense, honestly. In an AR model, it is forced to output a closing tag before providing the final answer. In diffusion, if it resolves the answer early across the block, it might truncate the canvas before explicitly materializing that formatting tag, which artificially drags down its automated benchmark scores.
Minor growing pains for a massive architectural leap.
Definitely. And that leaves us with a truly provocative thought to close on for you all listening. We have spent years in this industry obsessing over left to right, next token prediction. We assumed that sequential chain of thought was the absolute peak of AI reasoning.
Right, that it was the only way forward.
But if discrete text diffusion allows models to dynamically allocate compute on the fly and bidirectionally revise their own logical steps in parallel before outputting them, are we moving toward an era where the strict left-to-right next token prediction paradigm is seen as just a primitive evolutionary stepping stone? If models can now effectively draft, review, and rewrite their thoughts in a single parallel sweep, it really makes you wonder if AR's days at the absolute frontier of AI reasoning are numbered. Something to think about next time you're waiting for those tokens to stream in.